Welcome to American Shoulder and Elbow Surgeons Podcast. I'm your host, Peter Chalmers, a shoulder and elbow surgeon at the University of Utah in Salt Lake City. Before we get started, I should mention the views expressed in this podcast do not necessarily reflect the views of the American Shoulder and Elbow Surgeons Society, the University of Utah, or the institutions of any of our guests. Today, we're very excited to welcome Michele Pressacco to the podcast. Michele started as an engineer with Lima 30 years ago, and since then, he's risen through the ranks and is now the vice president of global new product development for Enovis. Along the way, he's been involved with implant design for many generations and iterations of implants, and we're very excited for him to share his experience working on the industry side. Michele, welcome to the podcast.
Good morning, everybody, and thank you for the opportunity to be here today.
So I want to start at the beginning. When did you first start working as an engineer?
Yeah, so I began my career as an engineer in Lima in 2002, immediately after completing my Master of Science in Mechanical Engineering. At that time, I joined Lima LTO, which is an acronym that stands for LUALDE, Mechanical Industry and Wins, while LTO stands for Lavorazione Titanio Ortopedico, which translates in English in orthopedic titanium machining. Back then, Lima was a relatively small family-owned company with around 20 employees. The operations were mainly related to the Italian market, with an annual turnover below 20 million. Despite its modest size, the company had a very focused expertise on processing titanium alloys because the background that the company had in the aerospace industry, and was using this legacy for orthopedic application. So joining Lima at that stage offered me a unique opportunity to work in a highly specialized environment where innovation and technical excellence were key, setting my foundation for my long-term career in the medical device industry.
So my understanding is that, Lima was originally involved in design and manufacture of helicopters. And when you joined, was there still any portion of the business that was doing any aerospace engineering, or at that point was it solely medical devices?
Yeah, that's correct. The company's roots trace back to Leopoldo Lualdi, the founder, who after the World War II developed one of the first helicopters made in Italy. So aerospace was one of the founding pillars of the business. In fact, throughout the 70s, Lima developed extensive expertise in processing titanium alloys, as I was saying before, specifically for aerospace application. And this advanced knowledge and high quality standards were later adopted to orthopedic implant production. And titanium became the of choice for hip and knees first, and later on for shoulder. In the years 2000, Gabriele Luarte, the son of the founder Leopoldo, strategically decided to focus exclusively on the orthopedic sector. So he carved out the orthopedic sector from the aerospace and the automotive business line. When I joined in 2002, I was employed by Lima LTO, which was at that point fully dedicated to orthopedics. So I personally started not in the aerospace, but in the orthopedic division, which, as I said, was built on a strong aerospace and automotive heritage.
So I think it's so interesting about this story is that it was the material initially that caused the shift within the company, the experience working with titanium. So tell us, you're a young engineer, you join this company that has this expertise with titanium. What have you learned about working with titanium as a material? Like, what are the things that we as surgeons should know about this material?
Yeah, indeed. Titanium has been in some way the common link between the aerospace and the orthopedics. And this link continues to be the case. The processing of titanium alloys and in particular the high requirements from the aerospace that were coming from the aerospace industry constituted in some way the backbone of Lima Orthopedics. What made Lima unique at that time, in my opinion, was it is vertically integrated. And this was instilled by the founder and his passion for mastering every steps of the process internally. So despite being a small company, Lima controlled the entire manufacturing chain, from forging, heat treatment, penetrant inspection, machining, welding, testing, everything was in-house. This environment was a tremendous learning ground for the engineers like myself. And so we learn a lot from taking the experience from those other industries. And for example, the heat treatment that is used to enhance the strength of highly stressed component, such as the metal back connector of the SMR shoulder, is very similar to the heat treatment that is used in the automotive industry for high stress application in the Ferrari engines. Another similarity is that the shot pinning that we use to increase the durability of the Morse taper connections is applied in the aerospace industry in the engine blades. And so those similarity goes on and on. More recently, metal 3D printing, as example, was applied in orthopedics, racing, and aerospace. Those were the three pioneering industry that take on board on this technology at the beginning of year 2000, and provided another area where the knowledge was in some way shared among the different industry. So overall, working with titanium at Lima was not just about mastering the material, but also understanding how aerospace, great precision and quality standard could transform orthopedic implant performance and reliability.
So that's fascinating. So you really were involved through the manufacturing. Now, I know also you were involved in the design side. You mentioned the SMR, and Lima's first foray into shoulder was with the SMR. Tell us about the design process for this.
Yeah, the SMR shoulder was launched back in 2002 in close collaboration with Professor Mario Randelli and his clinical team. The design of the SMR was an evolution of the Randelli's previous work in the 90s with the Randelli shoulder system. Professor Randelli's vision was to develop a truly modular implant platform. A platform that could be adapted even intraoperatively to meet the unique anatomical and pathological needs of each patient. That concept was at that time revolutionary because it provided surgeon flexibility to tailor implants even during surgery, allowing adjustment based on real-time assessment of the bone, the quality of the soft tissue. So this modularity of the system could accommodate a wide range of clinical cases, from trauma, anatomic to reverse configuration, and even complex cases, revision or even tumoral cases. All of that within a unique platform with interchangeable component. That was the design process behind the SMR shoulder. And clearly, the SMR's adaptability was its defining feature, enabling surgeon to build customized solutions on the fly, enhancing surgical outcomes and hopefully patient satisfaction.
And modularity it certainly provides us with advantages interoperatively because of its adaptability. You know, the traditional concern has been at the modular connections. What have been the kind of principles of making those modular connections work consistently for you?
Yeah, as you said, modularity was one of the core strengths of the SMR and has driven, in some ways, clinical success. However, the flexibility that comes with modularity brings drawbacks, complexity from one side, and also it needs to be properly optimized. Our guiding principle has been to ensure that all the modular connection deliver consistent, stable fixation while minimizing micromotion and wear at the interface, which in the end are the driving factors for the bioturbo corrosion, which may end up in the breakages of those modular connections. And in order to do that, we spent a lot of time to optimize the design, the precision of manufacturing, and also throughout testing to ensure the long-term durability of the component. So the goal for us has been always to balance the advantages of the modularity, which are the customization and the adaptability, with the need for mechanical robustness, simplicity during the surgical procedure.
Now, the SMR has really made use of that modularity to kind of, I would say, innovate on the glenosphere side. Like Lima, to my knowledge, was the first company to offer an all polyethylene glenosphere, sometimes called a reverse. So what are the advantages of that? Like, why would I want the glenosphere to be poly instead of the insert on the humeral side?
Yes, we call that solution the HP glenosphere that was introduced in the market back in 2005. And that solution was designed to address the issue of scapular notching that was in some way intrinsic in the Grammont design, especially when the base plate is not placed inferiorly. So the idea behind was that the HP glenosphere, made entirely from polyethylene, was designed to minimize the release of polyethylene debris in case of mechanical contact, which is implied in the progression of the most severe cases of scapular notching. On top of that, we have seen that with in vitro wear testing that this solution has shown lower wear if compared to the traditional bearing. Recent long-term studies, which has been published by the group of Professor Castagna, has confirmed not only the safety, but also the effectiveness of this solution. Additionally, the use of the hard solution on the reverse liner gave us the possibility to minimize the thickness of the socket and enable the development of what we call the lateralized liners. These lateralized liners reposition the humerals laterally, improving the toy wrapping and reduce the risk of scapular impingement. So in the end, the HP glenosphere has been introduced in the market over 20 years ago. It is the glenosphere that is mostly used in the international market, and we are actually currently in the process to register the solution in the US.
Now, there's always been this concern about kind of cold flow deformation of polyethylene in the body. So does this process not occur with more modern polyethylene? Like, why is this not a problem with an all poly glenosphere?
Yeah, well, cold flow deformation was not an issue, not even with the original material that we used back in 2005, which was a second generation poly, meaning an highly cross-link poly. And this is because the design of the glenosphere incorporates a titanium bushing that is preassembled at the factory and has the function to support the load and distribute those loads from the bushing throughout the component. So the bushing bears the mechanical load and stabilizes the polyethylene, preventing the deformation under the physiological stresses. So we have never experienced issues with cold flow deformation, I believe, because of this solution that is embedded into the SMR design.
And then Lima also offers a ceramic glenosphere. And what have been your kind of lessons learned working with ceramic as a material?
Yeah, well, Lima offers not a ceramic glenosphere, but a ceramic liner
I see. Okay.
to be paired with the HP glenosphere to provide a solution which is cobalt chromium frame. It is known that ceramic exhibit exceptional wear resistance and wear properties due to the hardness, the wettability, and all of that significantly reduce surface friction. So this is known. On the other side, there are concerns about ceramic breakages, although the high-strength ceramics like Bilox Delta and Ceramis, for example, have effectively addressed this historic concern, especially in the hip, and given the fact that the hip experience higher load, this is even more the case for the shoulder. However, ceramics remains a brittle material if compared to metal. And because of this, careful design optimization is required, especially at the contact interface, to minimize the concentration of the stresses. On top of that, rigorous in-process quality controls, like proof testing and dimensional control, are essentials, in my opinion, to mitigate the risk of fracture. So throughout our experience, we've learned that design precision and stringent manufacturing oversight are key to safely deploy this material and benefit of the superior wear properties in the shoulder implant.
So it sounds like it's a less forgiving material to work with, but that the precision is the key there. The newest iteration of that Lima offers is stemless. We've recently had Sean Churchill, who talked about the development of the first stemless component in the United States, as well as Michael Pearl, who talked about traditional problems in replicating the anatomy accurately with a stem. Tell us, what have been the challenges you face specifically in designing a stemless component?
Yeah, the SMR stemless was introduced in the market back in 2014, and it was conceived to be convertible. Convertibility as being one of the key elements, success factor of the SMR, and the input that we got from the design surgeon was to retain that heritage. So the primary challenge was not really the anatomic configuration, but was to ensure reliable fixation in the reverse configuration, which, as we know, experiences significantly higher mechanical forces. So achieving a stable implant bone fixation in a small component, that was something that, in my opinion, required innovation. And because of that, we developed what we call the proximal ring fixation concept, where basically the fixation is achieved in the peripheral region of the head at the resection level, where the head bone is harder. And so you have used that piece of bone to distribute the stress from implant to bone in a more effective way. Then we have leveraged the superior primary stability and osteointegration properties of our trabecular titanium technology. So the 3D printed lattice that was designed by Lima back in 2007 and was applied to the hip first and later on to the shoulder, in particular to the stemless design. Trabecular titanium is an highly porous titanium structure that was designed to enhance bone ingrowth. And furthermore, we combine the HP technology, which, as I said, give us the ability to minimize the thickness of the liner, with the aim to maximize the inlay of the component, thereby minimizing the bending moment that can compromise the fixation of the core. So the combination of all these elements, biological and mechanical strategies, overcome probably the traditional limitation in stemless reverse shoulder designs.
Yeah, it's fascinating to hear you talk about it, because there's so many design decisions that have downstream consequences there. One of the things you mentioned there is the use of 3D printing. What does 3D printing allow in implant design that was previously not possible? How does this change the way we design our implants? And what do we and the surgeons need to know about this process that might alter our implants?
Yeah, well, I've been involved in 3D printing for more than 25 years. in fact, I wrote my master thesis on metal 3D printing. By coincidence, while I was attending a conference at Synchrotron in Trieste, um, I attended a session that was held by Materialize, and I discovered at that time that there were application of that technology in the medical industry, and I was really fascinated about that. And this has been uh, the reason because I'm actually employed in the medical device industry, because I was so fascinated that I decided to apply at that time to a small unknown company that was called Lima, rather than cultivating my childhood dream, that was obviously to work in the automotive industry, in particular in the iconic brands like Ferrari and Lamborghini. So, as I mentioned, I had the fortune to continue to work at this technology when I was employed in Lima. And Lima has been the first company in taking this technology from rapid prototyping into mass production of orthopedic implant, and that was back in 2007. We invented the subarachnoid taking technology with the aim to improve osseointegration, and as a result, the long-term survivorship of the implants over other conventional coating technology. The first product, as I said, we applied this technology, was an acetabular cap, but since then we applied to other joints behind the hip, including the shoulder, the elbow, and more recently also the knee. The knowledge that has been developed over the past almost 20 years in master and 3D printed technology is now also deployed to ProMade, which is our division for custom-made solution that leverages the reliability of a process developed for off-the-shelf product to create bespoke solution to address the most challenging clinical cases. So going back to your questions, I believe that for surgeon, understanding that 3D printing enables complex geometries, enhanced bone ingrowth surfaces, and patient-specific design is probably essential, as it is clear that there is a shift in implant manufacturing from traditional subtractive technologies into highly customized additive methods.
You mentioned there that, and you mentioned a couple of times, applications of this technology outside of shoulder. I mean, for instance, I know you worked with our former chairman, Charles Salzman, on an ankle replacement. Tell us, what are the lessons you've learned outside of shoulder you've taken into shoulder? What are the lessons learned in the hip, knee, the ankle, elsewhere that we can take into shoulder implant design?
Yeah, you mentioned Dr. Salzman, so I will start from that. With Dr. Salzman, we initiated a collaboration to bring a clever idea in the ankle joint. The idea was to develop an insert nested ankle prosthesis. The aim was to reduce the overall amount of bone removal, and because of that, to purchase good quality bone to ensure long-term implant survivorship. There was a challenging design that would have leveraged, again, 3D printing because of this capacity to create complex structure and because of the superior bone ingrowth properties. But the complexity of the design, and especially the low thickness, because it was a kind of resurfacing of the material, lead to difficulties in machining those 3D printed blanks according to the design specification. So in that context, we came out with a new strategy to hold the 3D printed blanks. And now, for example, this technology is going to be used for a new complex shoulder 3D printed component, which is currently in development. So in general, there is a lot of cross-contamination among the different joints. And what we learn by working in one joint, more likely we'll find also other application in other joints. Another example I was mentioning, the shot peening process that we use to increase the mechanical strength of the most burrs was developed originally for the hip, where obviously the loads are significantly higher. Has been demonstrated to be effective in hip revision stems, and so now is used also in the shoulder. Same for the knee. We are working on the knee a solution to improve the tribology with advanced materials, and that solution will most likely find its own way also on the shoulder and later on the hip. So as I said again, there are multiple examples of cross contamination among the different joints.
Now, you mentioned when you joined Lima in 2002, there were 20 employees. Now, you've recently become part of Enovis, and that's, I'm sure, been a slow transition from this small family-owned business to this large multinational private equity-owned conglomerate. Tell us, what's that transition been like for you?
Yeah. Well, first of all, let me say that the integration with Enovis is going extremely well. Not only we have met, but we have exceeded all the strategic milestones that were established at the beginning of this transition. Enovis in general has a proven track record of successful acquisition and integration. So the synergy among the three legal entities, because here we are talking about an integration of three entities, Lima, Matis, and Enovis, which was formerly DJO, is strong, both from the geographical point of view, but also from the technical point of view. Geographically, the split is almost now 50-50, 50 US space and 50 international. Which helps to balance the global perspective and the operational agility. From a technological standpoint, Lima bring, as we was mentioning before, expertise in 3D printing, while Matix excels in ceramics and polymeric materials with ERM technology. And DJO, on the other side, contributes with his P-square platform. So before joining Enovis, Lima, since the early days, has grown a lot. It was owned by a private equity, a Swedish firm called QT, had already an international footprint with 24 subsidiaries, R&D and manufacturing plants in Italy and in the US. But now being part of Enovis, we benefit from a much larger scale, a significantly expanded global footprint. Obviously, the scale presents new challenges, particularly in aligning the interest of multiple stakeholders, while preserving the agility, which was typical of the smaller companies like Lima. So working also under a private equity ownership was different in terms of focus and investment cycles, which are often more short to mid-term oriented. Enovis, by contrast, provides a more strategic long-term vision for growth, innovation, and obviously that in combination with the resources of a global medical device player, which are significantly higher, are, from my perspective, motivating and offers exciting opportunities ahead of us.
What would you say you're most excited about then in the future of kind of shoulder implant design as you come at this now with new resources and obviously a much larger reach?
You mean what I say, what I'm excited about the future of shoulder implant?
Exactly, yes.
Yeah. Well, there are several areas of innovation that excite me. The first one is personalized care. Leverage the data that we have collected over the past 10 years of ProMade and the most recent advancement in 3D printing, with the aim to bring personalized patient-match implant to a larger patient population, in my opinion, is going to be a game changer. The freedom of fabrication that 3D printing offers enables the production of implants which are tailored to each patient anatomy. But obviously, the goal is to reduce the lead time and the cost always associated to custom implants. And we believe that leveraging data and artificial intelligence will help us in achieving this. The second element is severe bone loss. I believe there is still a lot that we can do to design new implants which are specifically aimed to address severe bone loss. This will involve combining data again, new techniques like topological optimization and 3D printing to create, in the end, implant that better fit the anatomy of those challenging cases that last longer and support more complex reconstruction. Third element, I would say, enabling technology. Advancing the preoperative planning with the aim also to integrate soft tissue modeling and use that plan for intra-op solution like augmented reality and robotics for precise execution is becoming a reality at this point. And I'm sure that these technologies will in the end enhance surgical accuracy, surgical workflow, and in the end will translate into hopefully better patient outcomes. And last but not least, the post-operative care. The use of data-driven rehabilitation protocols and post-op data collection to close the loop in the end. So to feed back the surgical planning and to drive surgical planning decisions, but also to drive rehabilitation strategies. Those things in the end will create a circular that may get us to better patient outcomes. So altogether, those advancements, in my opinion, will transform shoulder implant design and patient care in the years to come.
Well, it's certainly a future that I think we're all excited for. I think that it's just fascinating to hear your story, your transition from 2002 to today through titanium and polyethylene and ceramic, to talk about the design and the challenges with fixation between implant components and between implant and bone. It's I really appreciate your time. I know you have a lot going on with this transition with Enovis and the global expansion, and so I really appreciate you coming on to talk with us about us, and I'm confident that surgeons really will enjoy hearing your story. This is about all the time we have for the podcast, so thank you again, Michele, for coming on and joining us. For all of our shoulder and elbow listeners out there, don't forget to subscribe, and we will see you next time.